morning dear students. Today we are going to discuss 10th mathematics, that is first chapter, real numbers. In that the first concept is Euclid's division lemma. The concept of division algorithm. Given positive two integers a and b, there exists a unique pair of integers q and r satisfying the condition, that is a is equals to bq plus r. Here r is the remainder, q is the quotient and b is the divisor, and here a is the dividend. Here r should be more than 0 or equal to 0 but less than b, less than divisor, less than divisor. Here division lemma is used for finding the HCF of given two positive integers. This result was recorded in book 7 of Euclid's Elements. We discussed the page number 4 from the TS Government textbook. Do these problems. Find the HCF of the following by using Euclid's division algorithm. Here we have taken 3 problems. We will do by using Euclid's division algorithm. That Euclid's division algorithm, we knows that a is equals to bq plus r. Here r is the more than 0 or equal to 0 but less than divisor, that is b. Here 50 and 70 are the two positive integers given to us. Find the HCF of by using Euclid's division algorithm. So the greater number becomes our dividend is equal to the smaller number 50, here write in place of b, and 50 how many times divides 70, that is 1 time. The remainder how much left over, 50 ones are 50, left over 20. So remainder 20 it becomes. Now consider the divisor 50, do the division with 20. So 50 is equals to 20 2s of 40, remainder becomes 10. So 20 2s 40, remainder 10, that is equals to 50. Now next step, now do the division of 20 with the remainder 10. So 10 2s are 20, remainder got we have 0. So further we can't proceed. So till here we can stop it when remainder is 0. At last stage the divisor 10. So that divisor becomes our HCF of given two integers. Now the next second problem. Here the greater number is 96, so write 96 here. Do the division by 72, this is a smaller number. So 96 divided by 72, it gives only one time it goes. So 96 minus 72 is 6 minus 2 is 4, 9 minus 7 is 2, 24. So now the divisor is 72, 72 divided by, do the division by 24, that is a remainder. So 24 into 3 times what happens? 3 4s are 12, 3 20s is 60, 3 4s are 12. So 3 times it goes. So remainder becomes 0. So here we can conclude that the last divisor 24. So 24 is the HCF of given two positive integers, that is 96 and 72. So HCF of 96 and 72 is 24. The last divisor is 24. Here we got remainder as 0. So that last stage the divisor becomes here HCF of given two positive integers. Third one, 300 and 550. Here the bigger number is 550. Write as a dividend. 550 is equal to the smallest positive integer, that is here 300. So 300 divides 550 only once. The remainder is 300 subtract from 550, that is 250. 250. Now do the division of 300 with remainder 250. 250 also divides 300 only one time. The remainder is 50. Remainder is 50. Now do the division 250 with the remainder, that is 50. So 50 divides 250 5 times. So 0 is as it is, 5 5s are 25, remainder gives 0. So at last 50 is a divisor, so that therefore HCF of given two positive integers, that is 300 and 550 is 50. Is the HCF. Next problem, fourth problem, given 1860 and 2015. So greater number you can write as a dividend. 2015 is equal to 1860 into 1 time, the remainder becomes 155. Now the do division of 1860 and the remainder 155. 1860 into 12 times you will get 1860. So remainder is 0. Here we have done a division. So when remainder is 0, further we can't proceed, so that we can stop till here. At last stage, the divisor becomes your HCF of given two positive integers, that is 1860 and 2015 is 155. This is a method of Euclid's algorithm to find the HCF of channel VictoryMath1729. Today we are discussing the 10th mathematics, real numbers, chapter number 1. So earlier we have discussed the Euclid's division lemma. From that we have discussed do these problems. Next think, discuss in page number 5. The question is can you find the HCF of 1.2 and 0.12? Here given numbers are decimals. So the condition is we cannot find the HCF of 1.2 and 0.12. Why? Because these are decimals. Hence we can find only the HCF for the positive integers. So since the given numbers are not positive integers, so that hence we cannot find the answer for these two given numbers. Next we enter into exercise 1.1. Use Euclid's algorithm to find the HCF of 900 and 270. Second one 196 and 38,220 and 1651 and 2032. So first problem, we can see the solution of this. The condition is first dividend the largest number, here 900. So the condition you can write that first, Euclid's division lemma. The condition is A is equals to PQ plus R. Here R should be, here R is equal to 0 or more than 0 but less than B. This is a condition. Put this condition in rectangular box. Now the process of this one, the greater number you can write as A. Now 900 divided by the smallest number, that is 270, into 270, how many times it divides 900? So 0 0 as it is, 27 3s are 81, 8 10. So remainder will be 90. So now the next step is, now do the division 270 with the remainder. So now 270 write as dividend, do the division by this remainder. In 9 table 27 3 times it goes, 9 3s are 27, 0 for 0 as it is, remainder is 0. So till here until the remainder is 0, still further we can't do the division. So till here we can stop it, and at last stage we have 90, that 90 becomes your HCF. So therefore HCF of given two numbers, what are those two? 900 and 270. 900 and 270 is 90. This is a solution. Coming to 196 and 38,220. So largest number we can write first, 38,220 is equals to, do the division by 196 into how many times it goes. Here which is the largest number, so for that you can go for division. So do you know, if we find the GCD of this one, then we can easily write this Euclid's division lemma. Here 38,220, 196. One time you can take here, one time 19 2s are 38, it gives So 38,220 is a little large number, so that you can do the division besides. So how many times it goes? Directly you know very well about the division. So 196 into 195 you are getting remainder as 0 here. So 196 into 195 you are getting 38,220. So directly you can write a 195, remainder you are getting 0. So HCF what might be that? So HCF becomes 196. HCF is 196. Coming to third one, 1651, 2032. So largest is 2032 is equal to 1651 into 1 time. What might be the remainder? So 2 minus 1 is 1. 3 minus 5 not possible. 13 minus 5 8. Here 19 will be 19 minus 16 is 3. 381. So now the division 1651 divided by 381. So into how many times it goes? So here also you can do that division 1651 divided by 381. 381 how many times? Mostly 5 times we check. 5 ones are 5, 5 8s are 40, 5 3s are 15, 15 19 not 5. So 4 times you can check. 4 ones are 4, 4 8s are 32, 4 3s are 12, 12 plus 3 15, 24. So 4 times 15, 24. By subtracting, what do you get? Here 11 minus 4 7, here 4 minus 2 is 2, here 127 will be 127 in the sense here not possible, no? So 4 times remainder is 127. Now do the division 381 with the remainder 127. How many times it goes? Almost it is 3 times it may be. So 3 times 127 into 3 times what happens? 3 7s are 21, 3 12s 36, 38. So we are getting 3 times we are getting 381. So remainder becomes 0. So until the remainder 0 we done Euclid's division lemma. So at last stage 127 becomes your HCF. So HCF of 1651 and 2032 is 127. This is the answer. So today the problem is exercise 1.1, second problem. The question is, show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5. So here we have the Euclid's division lemma, that is a is equals to bq plus r. Here r is a remainder, that should be more than 0 or equal to 0 but less than b. Here b is the divisor. So that given number is equals to 6q plus 1. 6q plus 1. Here in place of b we have 6. So r might be equal to 0 or less than 0, not less than 0, more than 0 but less than 6. Means r values should be, r is equals to 0, 1, 2, 3, 4, 5. Why it is still 5 in the sense less than 6 means still 5. So a is equals to, a value becomes 6q or 6q plus 1 . If r is 1, 6q plus 1, 6q plus 2 or 6q plus 3, 6q plus 4, 6q plus 5 till here. Next here a is equals to 6q, a is equals to 6q plus 2, a is equals to 6q plus 3, not 3, it's 4, these are divisible by 2, so that these are even numbers, even integers, and divisible by 2, divisible by 2. Next, here A is equals to, next set, 6q plus 1, A is equals to 6q plus 3, or A is equals to 6q plus 5. These are odd integers, and not divisible by 2, not divisible by 2. So therefore, any positive integers can be written as, any positive integer can be written as 6q plus 1, or 6q plus 3, or 6q plus 5. Therefore, hence showed. Any positive odd integer can be written as 6q plus 1, 6q plus 3, or 6q plus 5. That we have to show. Here shown. Here 1 is an odd number, 3 is an odd number, 5 is an odd number. So that these are not divisible by 2. Hence the positive integer cannot is of the form 6q plus 1, 6q plus 3, 6q plus 5. And our next problem is third problem, that is use Euclid Division lemma to show that the square of any positive integer is of the form 3p or 3p plus 1. So the solution, we knows that division algorithm. So let a be any positive integer. We apply division algorithm with a and b is 3. Since remainder is more than 0 or equal to 0 but less than 3, then the possible reminders are 0, 1, 2. That is, a can be 3q, 3q plus 1, or 3q plus 2. Here reminders less than 2, less than 3, in the sense the reminders are 0, 1, 2. So 3q plus 1, 3q plus 0 means 3q, 3q plus 1, and 3q plus 2. So remainder till 2. Here what is q? Q is the quotient. Now 3q whole square, square of any positive integer, no? So that 3q, first one 3q whole square, that we can write as 9q square. So take out 3 as common, here 3 outside, so the remaining 3q square. So 3 times of 3q square gives 9q square, so that in place of 3q square we can take as one integer, that is p. So 3q square we can write as 3p. So p is here, p is equals to 3q square. Next again 3p plus 1. So that here the second one 3q plus 2. Here 3q plus 2, no, 3q plus 1. So 3q plus 1 is a whole square is equals to, this is in the form of a plus b whole square. That is equals to, we have that a square plus 2ab plus b square. So write in that form, 3q square plus 2ab. In place of a we have 3q, in place of b we have 1. So instead of that you can write 3q into 1 into 2. So b square is nothing but 1 square. So 3q whole square is nothing but 3 square is 9, q square is as it is, plus 2 3s are 6, 6 1s are 6, q plus 1, 1 square is 1. So from these two terms take out 3. Why? We have to write that in the form of 3p plus 1. So that 3 times of 3q square plus 3 2s are 6q plus 1. So take this as a one positive integer, that is p. Here 3p plus 1. So we have written the second one 3q plus 1 whole square. Square of any positive integer is of the form 3p plus 1 also. So that we need to show, that is 3p and 3p plus 1. Hence showed, that is HP. Our next problem is use Euclid's division lemma to show that cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. This is our problem. Take any positive integer, cube of that, and that should be, you have to write in the form of 9m, 9m plus 1 or 9m plus 8. So let a be any positive integer, a is any positive integer. We apply that division algorithm with a and b is 3. B is 3. Since r is greater than or equal to 0 but less than b, here 0 less than or equal to r less than b. The possible reminders are r is 0 or more than 0 but less than b. Here b is 3, so that 0, 1, 2 till 2 we have to take. Why? Because r is less than b. So less than b in the sense less than 3, that is 2. Now that is a can be then 3 cube plus 0. 3 cube plus 0 is nothing but 3 cube. 3 cube plus 1 and 3 cube plus 2. Here 0, 1, 2 are the reminders. Where what is q? Q is the quotient. Now take this positive integer a is equals to 3 cube, then cube on both sides. So a cube is equals to 3 cube whole cube. 3 cube whole cube is nothing but 3 cube is 27, q cube is as it is. Now that you can write in the form of 9m. So 9, put it outside, 9 3 is 27, so that 9 times of 3q cube. So 9 is as it is, 3q cube take as that integer, that is m. So now we have written, which can be written as a cube is equals to 9 into 3q cube, that is we have written as 9m. Here m is nothing but 3q cube. Next again, now a is equals to 3 cube plus 1. So cube on both sides, a cube is equals to 3 cube plus 1 whole cube. This is in the form of a plus b whole cube. A plus b whole cube. So a plus b whole cube is equals to a cube plus 3a square b plus 3ab square plus b cube. So write this in the form of this one. So a cube, a is nothing but 3 cube. So its cube is 3 cube is 27, q cube is as it is, plus 3a square b, 3 into, in place of a we have 3q, its square, into b, that is 1. So 3 is 3 into 3q whole square into 1 plus 3ab square, 3 in place of a we have 3q, in place of b we have 1, so its square, plus b cube, b is nothing but 1, its cube. Now 27 cube, 3 3s are 9, 3 square is 9, 9 into 3, 27 again, 27 q square, 3 3s are 9 into q into 1 square, that is 1. Here 1 square is 1, 3 3s are 9 cube, 9 cube, 1 cube is 1. Next, now take the common of, take out 9. Why? Because we have to write that in the form of 9m plus 8. So take out 9. 9 times 3 is 27, q cube is as it is, plus 9 times of 3 is 27 q square plus 9 into q. So we have taken out 9. So the reminders we have written here plus 1 here. So this total term we can take as one positive integer, that is one alphabet, that is m. So that is in the form of 9 times of m plus 1. So we have written the second positive integer, cube of any positive integer, we have written as 9m plus 1. So m is equals to this part. Next we have a is equals to 3q plus 2. A is equals to 3q plus 2. Cubic on both sides. So a cube is equals to 3q plus 2 whole cube. So again this is in the form of a plus b whole cube. That is equals to, we know that a cube plus 3a square b plus 3ab square plus b cube. That we can write in the form of this. So 3 cube is 27 q cube plus 3a square b, 3a square b, 3 times of a square, here 3 square q square it becomes, that is 3 into 3q into 2. So 2 into 3 square is 9, 9 3 is 27, 27 2 is 54, q square you will get. Second part, that is 3ab square, 3 into a is as it is, 3 3 are 9, b square is nothing but 4. So 9 4 is 36, q will get. Again 2 cube is nothing but 8. Now this part you can write in the form in terms of 9m plus 8, so that we have common, take out common as 9. Here 9 multiples 27, 54, 36. So 9 outside, 9 3 is 27, q cube is as it is, plus 9 6 is 54. Next plus 9 4 is 36, plus 8 is outside. Here this part you can take as one alphabet, that as m. M is equals to 9 3 q cube plus 6 q square plus 4 q. So that is we have written as 9m plus 8. So first positive integer we have written as 9m. Second positive integer we have written as 9m plus 1, and third positive integer we have written as 9m plus 8. So that we can say that we can show any cube of positive integer in the form of 9m, 9m plus 1, 9m plus 8. Hence show. Question is, show that, fifth question, show that one and only one out of n plus 2 or n plus 4 is divisible by 3. Is divisible by 3. So here, if it given numbers are n plus 2 or n plus 4. So if we take a n is equals to 1, the numbers becomes 1, 1 plus 2, 1 plus 4. So this is as it is 1, 1 plus 2 is 3, 1 plus 4 is 5. So among these three numbers, only 3 is divisible by 3. Only n plus 2 is divisible by 3. Only n plus 2 is divisible by 3. Next, if n is equals to 2, n becomes 2, n plus 2 becomes 2 plus 2, and n plus 4, that is 2 plus 4. 2 plus 4 is 6. 2 plus 2 is 4, 2 plus 4 is 6. Among these three digits, three numbers, only 6 is divisible by 3. Only 6. 6 is nothing but n plus 4 is divisible by 3. Only n plus 4 is divisible by 3. Next, if n is 3, if n is equals to 3, the n becomes 3, n plus 2 becomes 3 plus 2, n plus 4 is 3 plus 4. So among these three numbers, first one 3, 3 plus 2 is 5, 3 plus 4 is 7. Among these three numbers, only 3 is divisible by 3. So if only n is only n, 3 is nothing but only n value. Only n is divisible. Only n is divisible by 3. So here, if by taking n value as any positive integer, here 1, 2, 3, so on, among three numbers, only one is divisible by 3. So therefore n plus 2 or n plus 4, among these three, only one and only one number is divisible by 3. Among these three, only one number is divisible by 3. Divisible by 3. Here note is, in any three consecutive 3 consecutive positive odd integers one number is multiple of 3. In any 3 consecutive positive even integers one number is multiple of 3. Hence n plus 2, n plus 4, only one number is divisible by 3. So therefore one and only one out of n plus 2, n plus 4 is divisible by 3, hence showed. Please do subscribe my channel VICTORYMATH1729, like, share and comment in sections. Thank you.